All right, welcome back to Engineering 270. This is lecture number 2. In this lecture, we want to start talking about a bit of the software we're going to be using with the PIC processor and a little bit about what assembly language is and what machine language is, how we actually program a PIC processor. We're not going to get into a lot of detail yet, but we're going to be heading towards that in lecture 3. So software-wise, we're going to be mainly working with a piece of software called MPLAB. And this is free software. You can download a version called MPLAB X. It runs under Java, and you can download this and run it on your own machine, or you can run this on the lab machines in the collaboratorium. So MPLAB and MPLAB X, these are what we call IDEs, Integrated Development Environments, which means they take all the different tasks that you're going to use in working with this software and combine them into a single package. So what kinds of things do we want to do? Well, we want to be able to edit code. So we're going to have an editor. That editor is going to do syntax checking. So it understands what we're typing and it'll tell us if we're making mistakes. We're going to be able to do assembly. So we're going to be able to take our code and say, okay, turn this into ones and zeros. We're going to be able to debug our code. We're going to say, okay, we've written our code, we've assembled it. Let's see what it would do if we ran it on hardware. And it will simulate the hardware for us and let us do some analysis. It will also let us load our code into the PIC processor so that it actually becomes a piece of hardware that does whatever our program asks it to do. It will also let us unload the ones and zeros from a PIC processor into memory, and will also let us disassemble. So in some sense we can go back to looking at the assembly language. But this is going to be our main tool flow. We'll write code, check the syntax, assemble it, maybe run it through a debugger, and then load it into a PIC processor, and then our chip is live. So integrated development environment means all these things are being done in a single piece of software. That's MPLAB X. All right, so let's talk about what it actually means to program a microprocessor. What does a microprocessor do? I mean, I've said it understands ones and zeros, but what does that actually mean? So if we were to look at the data sheet, right, here's a block diagram of what we could call a data path. And it's very complex. There's lots of things going on here, lots of arrows, lots of acronyms. But in the text, there's a simpler version of this, which looks like this. This is basically what a microprocessor looks like. There's a program memory that basically says, what are the instructions that you want me to execute? Okay, this is a memory. You can specify an address and say what's stored at that address in this memory. And your address is, something like 0, 14, 26. Each address has a different set of ones and zeros, and those ones and zeros, those correspond to what we think of as a single instruction. So instructions are taken from the program memory, and the hardware in the PIC processor looks at those instructions and does whatever they ask it to do. And what do those instructions ask it to do? Well, for the most part, they ask it to read something from memory, from a data memory, maybe make some change on it, and then write it back into some location in data memory. Or it might ask it to perform some sort of input-output operation. Take the contents of some location in memory and send it to this location in the outside world. Or read something from the outside world and put it into some location in memory. Now, how do you move from instruction to instruction? There's something called a program counter. That's a PC. So the program counter says where is the next instruction in memory that I should be reading from. And in the PIC processor, instructions are stored at even locations. So the first instruction is location 0, the next is location 2, then 4, and so on. So the program counter goes into an adder which adds 2 to the current value and loads the new value back into the program counter. So each time the program counter goes through this path, it gets incremented by 2. And when the next instruction is read from wherever the program counter is pointing, it's reading the next instruction from program memory. And this is a process that we can think of as fetch, decode, execute. This is the classic behavior inside a CPU, fetch, decode, execute. It's a 3-step process. Fetch is basically saying, okay, take the program counter, use that to address the program memory, read an instruction. Okay, so it pulls the ones and zeros out corresponding to that program counter. Decode says, what does this instruction want us to do? Because the instruction is just a bunch of ones and zeros. Does it want me to read something from memory, write something to memory, do some I/O? It interprets that set of ones and zeros, it decodes it into what the intent is, and then it actually executes it. That's the third piece. So it performs whatever operation is indicated by that instruction. And then the program counter, which has been incremented by 2, is used to fetch the next instruction. And this just repeats over and over and over. Fetch, decode, execute, fetch, decode, execute, goes on forever. And it's driven by the PC, the program counter, right? That's what tells it where to fetch the next instruction from. We'll deal a lot with the program counter. Okay, well, there's 5 types of instructions. And they come into 3 categories. So the first category is what we call byte-oriented instructions. The second category is bit-oriented instructions. The third is literal instructions. That's the first 3 classes of instructions. An example of a byte-oriented instruction would be read the piece of data stored at this location in the data memory, add 1 to it, and then write it back into that location. So your instruction might say, okay, go to data memory location 12, read the 8 bits that are stored there, read the byte that's stored at that location, add 1 to that value that you read, write it back into data memory at the same location. That's a byte-oriented instruction. A bit-oriented instruction might say, read the contents of data memory at some particular location, set the 3rd bit to 0, and write it back. And a literal instruction might say something like, take the number 7 and store that at a particular location in data memory. Okay, at this point I should make something clear that has been alluded to. There's a program memory and there's a data memory. And these are very different from each other. Program memory has instructions. Data memory has data. Not surprising. So this is also called instruction memory instead of program memory. This has the instructions that say what do we want to do to the data memory, okay? But they're physically separate memories, and we'll talk later about why that is. So of our 5 types of instructions, byte, bit, and literal instructions, basically read and write data memory. Okay, our 4th type of instruction is called control instructions. And control instructions change how instructions are fetched from program memory. They can do things like, for example, change the program counter. So that instead of simply being incremented by 2, it might get set to some other value. So byte, bit, and literal instructions relate to what we want to do with data memory. Control instructions, in some sense, affect what we do with program memory. And then the 5th type of instruction is called a memory block instruction, and we're not going to really worry about that too much. So we're going to mostly deal with these 4 types. All right, one more detail to point out. We have program memory and we have data memory. That's all sitting inside this chip, right? If we go back to this picture from the data sheet, all right, here's the program memory. Okay, so it's 4,000 bytes, which will turn out to be 2,000 instructions. And here is the data memory. Okay, and our data memory is about 128 locations. It's very small. But those are both inside the physical chip. How do we do things like turn on an LED? How do we read a value from a switch and use that to change the contents of data memory? So we use a technique called memory mapped I/O. And here's the setup. In our data memory, remember data memory is addressed, so there's different locations for each piece of data. But there are some locations where we look like we're addressing some location in data memory, but in fact, this is some sort of I/O port. This is something other than just a location in memory where we store a value or read a value. This is actually a piece of hardware that we pretend is a piece of memory, but when we write to that particular location in memory, we might actually be setting the voltage level on a pin somewhere. Or we might be setting a piece of information that's going to be used by a timer or the oscillator subsystem or something else. So we have this idea of memory mapped I/O. All right, so that's the end of lecture 2. So lecture 3, we're going to talk about this memory mapped I/O in a little more detail, and then we're going to start looking at the actual coding of byte-oriented instructions.